You're given an array of stock prices where each element represents the cost on a specific day. Your goal is to find the maximum profit you can achieve by buying on one day and selling on a later day. If no profit is possible, you return 0. For example, with prices like 7, 1, 5, 3, 6, and 4, the best move is buying at 1 and selling at 6 for a profit of 5. A naive approach would check every possible pair of buy and sell days using nested loops. This means comparing the current price against all future prices to find the highest difference. While this works, it wastes time by re-evaluating pairs that have already been considered or are clearly suboptimal. We need a way to make decisions in real time as we scan the list. The efficient pattern here is tracking the running minimum price alongside a running maximum profit. As we iterate through the array, we update the lowest price seen so far and simultaneously calculate the potential profit if we sold at the current day. This allows us to solve the problem in linear time with constant space. Let us trace the example array 7, 1, 5, 3, 6, 4. We start with a minimum price of infinity and 0 profit. At index 0, price is 7, so we update our minimum to 7. At index 1, price is 1, which is lower than 7, so we update our minimum to 1. At index 2, price is 5. The profit if we sold now is 5 minus 1, which equals 4, updating our max profit to 4. At index 3, price is 3. Selling here yields 2, which is less than 4, so profit stays 4. At index 4, price is 6. Selling here yields 5, updating our max profit to 5. Finally, at index 5, price is 4. Selling here yields 3, leaving the max profit at 5. We begin by initializing two variables. One for the minimum price found so far, set to the maximum integer value, and another for the maximum profit, set to 0. This setup ensures that any valid price will update the minimum, and any positive profit will update the result. We then loop through each price in the input array using a standard for each iteration. This single pass allows us to process every day exactly once, maintaining our state as we go. Inside the loop, we first check if the current price is smaller than our recorded minimum. If it is, we update the minimum price to this new low, representing a better potential buy day. Next, we calculate the potential profit by subtracting the current minimum price from the current price. We compare this calculated profit against our stored maximum profit and update the maximum only if the new value is higher. You might wonder if a hash map or stack could help, but those structures are unnecessary here. We do not need to look up previous indices or manage a history of prices. We only care about the absolute lowest value encountered up to the current point in time. This approach runs in linear time because we visit each element exactly once. The space complexity is constant since we only store two integer variables regardless of the input size, making it significantly more efficient than the quadratic brute force method. The key takeaway is to maintain a running minimum when you need to find an optimal pair with order constraints. This pattern applies to many problems where you must compare current values against the best historical value. Try coding this solution yourself to solidify your understanding of single-pass optimization.